The final part of our cooperation experiment reveals how we are able to share intentions in a way that apes never can. We are on the verge of finding the barrier that divides humans from apes. We're trying to find out if our ape cousins are capable of cooperating and helping others the way humans do. In our final experiment, a researcher places a piece of food under one of two cups. The chimp has to choose the cup where the food is hidden. The researcher reaches for the cup with the food. And the chimp goes straight for it.
You set up a situation where you're competing with the chimpanzee and you reach for it, like you're trying to get it yourself in competition with the chimp. Then they see that and they make the inference that must be where the food is. If he's trying to get in there, that must be where the food is.
But just a slightly different gesture changes everything. Instead of reaching for it, the researcher points towards where the food is hidden. Half the time, the chimpanzee picks the wrong cup. It doesn't understand that the researcher is trying to help it.
Perfect.
I don't think chimpanzees quite understand that you're trying to inform them of something helpfully. In their natural state, chimps don't just point to some food for another chimp and say, here's some food if you'd like it. I don't want it right now, you can have it.
Chimpanzees apparently only understand intentions from a selfish viewpoint. They only cooperate if they think they will gain something from their actions. Here's the same test, this time with an 18-month-old child. The child gets the idea immediately.
Human children come into the world automatically assuming that people want to be helpful and to show them things and share things with them, even food that the person who's pointing could take for themselves.
There's something in our genetic makeup that from an early age allows us to work together towards a common goal. We read and trust each other's intentions. It seems this could be what makes us human.
Humans cooperate and communicate in especially complicated ways in forming social institutions like universities and government, in building buildings, in sports teams, in wars. Our armies are quite cooperative also. So being able to help one another and to do things for one another's benefit and stuff that humans are especially prone to do.
On the journey between human and ape, something changed. At some point, our brains began to develop differently. Now, scientists think they know when and how this change happened. We've come to Philadelphia, where this discovery was made by pure chance. Hansel Stedman at the University of Pennsylvania studies muscular dystrophy. To understand the disease better, he decided to compare human muscle cells with those in the great apes. He noticed something unusual in some of the cells in one particular muscle, the jaw muscle. He took a thin slice of chimpanzee and a thin slice of human jaw muscle and compared them under a microscope.
We're looking at a razor-thin section of one of the jaw-closing muscles from a great ape.
These red cells seen in cross-section are a chimpanzee's biting muscle fibers. But when Stedman looked at the human jaw muscle, the difference was immediately obvious. The human biting muscle fibers at the bottom are 1/3 the size of the great apes. This isn't just an isolated case. Every human jaw muscle looks the same. Stedman has discovered that in the distant past, a genetic mutation occurred. It made our ancestors' jaw muscles much weaker than those of the other apes. You wouldn't think that a weaker jaw could be an advantage back in the prehistoric era. But incredibly, it's this genetic mutation that could be responsible for something even more amazing. The secret lies in the way muscles attach to bones, in this case, the skull.
If you take a look at this orangutan skull, this is an adult male, this illustrates very nicely that muscles leave an indelible mark on the bones where they attach to them. And so this dramatic cresting, which is so magnificently developed in this specimen, shows you that there was a very powerful jaw-closing muscle in this individual.
All the great apes have a crest along the top of their skull. They need it because their strong jaw muscles need a firm anchor. But the thick skull has another effect. It acts like a rigid and inflexible cage on the brain. In humans, our weak jaw muscle exerts far less pressure on the skull.
If we take a look at this adult male human, in comparison, you can see the remarkable contrast. The skull surface is actually quite smooth. There's a very tiny residual mark, but in fact, this muscle was a very thin wafer, feeble almost by comparison with the orangutan that we just looked at.
Around 2 million years ago, there were several hominid species walking the earth.
You have populations with individuals as dramatically different looking as this, literally living cheek by jowl.
These skulls belong to two different hominid species living together over 2 million years ago. Australopithecus boisei on the left and Homo erectus on the right. Anthropologists are convinced that genetic mutation occurred in one of these hominids, weakening the jaw muscle and allowing the skull and brain to expand. But which one? The Australopithecus has a large, ape-like jaw muscle, while the Homo erectus has a much smaller, human-like jaw muscle. It's this one that has the genetic mutation.
The other dramatic difference, obviously, is in the size of the brain case.
Homo erectus has a brain that's 50% larger than Australopithecus boisei. But when did this happen? By comparing how genes vary in different species over millions of years, Hansel Stedman has calculated that the strong jaw muscle mutated into the weaker muscle in our ancestor Homo erectus about 2.4 million years ago. It's one of the most important moments in our evolutionary history. And it's all down to a single genetic mutation.
That occurred in one individual at one point in time when there was a gene pool of interbreeding animals that all had the normal version of this gene. And yet, with the passage of time, the only surviving version of that gene in humans is the mutant version. It eclipsed all of the others that were in that breeding pool at that time through the process of genetic fixation.
A single genetic mutation, but powerful enough for our ancestors to outcompete all other hominids. But how did these early ancestors of ours survive with jaw muscles 10 to 50 times weaker than their rivals?
If you know you're going to lose a jaw-to-jaw combat, then avoid jaw-to-jaw combat altogether. Find some other way to annihilate your competitors.
And that's what our ancestors did. They switched from brawn to brain. Blessed with a larger brain, our ancestors began to cooperate. They shared their plans, developed complex social structures. This was the first step on a journey that would ultimately propel us into a different world. But before modern humans like us would emerge to conquer the planet, we needed one more ingredient to really take off.